Okay, I had to send a new link to the YouTube Live. So we'll see how that goes. We were talking about the arc length of this curve, and we found that we needed to go from 0 to 2 pi to find the complete arc length. We need to know what dr d theta squared is, and then add that to r squared to put inside the square root. So let's first find dr d theta, where r is 1 minus sine of theta. So this is just negative cosine of theta. And we're going to square that. We're also going to square r, so let's do that here. R squared is 1 minus 2 times sine of theta plus sine of theta squared. Okay, and when we square dr d theta, we get cosine of theta squared. So this will become cosine of theta squared and then plus 1 minus 2 times sine of theta plus sine of theta squared. Cosine of theta squared plus sine of theta squared is 1. So we're going to get 1 plus 1. I'll go ahead and put that in here. Yes, so 1 plus 1 minus 2 times sine of theta is 2 minus 2 sine of theta. Okay, so that's a setup. I want to take it a couple of steps further. Notice that the graph of r equals 1 minus sine of theta is symmetric with respect to the vertical axis. So if we integrate from negative pi over 2 to pi over 2, and then multiply that by 2, that will give us the entire arc length. So rewrite this. Instead of going from 0 to 2 pi, we're going to multiply 2 times the definite integral from negative pi over 2 to pi over 2. And then we're going to multiply this integrand by 1 in the form the square root of 2 plus 2 sine of theta divided by the square root of 2 plus 2 times sine of theta. Okay, and when we do the algebra and arithmetic, so notice the denominator is the square root of 2 plus 2 sine of theta. And that can be written in the integrand as the quantity 2 plus 2 sine of theta to the negative 1/2. And when we simplify the square root of 2 minus 2 sine of theta times the square root of 2 plus 2 times the sine of theta, we're going to get the square root of 4 minus 4 times sine of theta squared. But 4 minus 4 times the sine of theta squared is, using a Pythagorean identity, is 4 times the cosine of theta squared. And when we take the square root of 4 times cosine of theta squared, we're just going to get 2 times cosine of theta. So did you follow that? So using the substitution rule, we're all set up to compute the integral, because if u is 2 plus 2 sine of theta, du is 2 cosine of theta d theta, right? Did you follow all of that? If you just do the arithmetic and use a Pythagorean identity, you'll get this. This part of the integral is what comes from this denominator. So I might as well just take it one step further. We can compute the antiderivative. So we're going to add 1 to negative 1/2 and then divide by that same number. We're going to divide by 1/2, which is the same as multiplying by 2. And then we'll have 2 plus 2 times sine of theta to the positive 1/2, and then evaluate that between negative pi over 2 and pi over 2. And that won't be too hard for you to do, so I'll leave the rest of that for you to evaluate. Okay, the next one, find the arc length of r equals cosecant of theta for values of theta between pi over 3 and 2 pi over 3. So we need to know what the derivative of r with respect to theta is. So what's the derivative of cosecant of theta with respect to theta? Well, it's negative cosecant of theta times cotangent of theta. So how can you remember that? I'll just do a quick calculation. If r equals cosecant of theta, that's 1 over sine of theta. And then to take the derivative, we can use the quotient rule, dr d theta. So the derivative of the numerator is 0 multiplied by the denominator, and then minus the numerator multiplied by the derivative of the denominator. The derivative of sine of theta is cosine of theta, divided by the square of the denominator, so sine of theta squared. So we get negative cosine of theta divided by sine of theta squared. But somebody at some point decided it's better to think of negative cosine of theta over sine of theta squared as negative 1 over sine of theta times cosine of theta over sine of theta. So we're all in agreement so far? And negative 1 over sine of theta is negative cosecant of theta, and cosine of theta over sine of theta is cotangent of theta. So this has become the conventional way to write the derivative of cosecant of theta. It's not the only way, but it's the one that you see the most often. Okay, then we're going to square that in a minute, but we also are going to square r squared. So the arc length then is the integral from pi over 3 to 2 pi over 3, and the square root of dr d theta squared. When we square this, we'll just get cosecant of theta squared times cotangent of theta squared plus r squared, which is cosecant of theta squared. Then we'll do a little bit of manipulating. So inside the square root, we can factor out cosecant of theta squared, and we're left in parentheses cotangent of theta squared plus 1. And now what? Using a Pythagorean identity, we can replace cotangent of theta squared plus 1 with cosecant of theta squared. So inside the square root, inside the square root, we're going to have cosecant of theta squared times cosecant of theta squared. So that's just cosecant of, I'm all messed up, cosecant of theta to the fourth, and then the square root of cosecant of theta to the fourth is cosecant of theta squared. And an antiderivative of cosecant of theta squared is negative cotangent of theta, which we will evaluate between pi over 3 and 2 pi over 3. If it helps, you can think of negative cotangent of theta as negative cosine of theta over sine of theta, and then evaluate the integral that way. So I'll leave the rest of that for you to do, but I'll just go ahead and write down what I just said. You can rewrite negative cotangent of theta and think of it as negative cosine of theta over sine of theta from pi over 3 to 2 pi over 3. Okay, let's go ahead and start the chapter 11 material. Section 1 in chapter 11. This is the section on sequences. So there's a fair amount of reading. We'll have a little bit of interacting in between. But we'll start with this. Sequence is a list of numbers in a definite order. There are various notations for sequences. So here's one way, a sub 1, comma, a sub 2, and so on. The 3 dots mean that it continues infinitely. The same sequence can be represented this way in brackets, a sub 1, a sub 2, a sub 3, and then dot, dot, dot means that it continues infinitely. Or you can just write in brackets a sub n. If you want to be a little more explicit, you can write in brackets a sub n, indicating that n goes from 1 to infinity. We'll look at some examples of sequences, but just keep in mind, even though we often start with a sequence with n equals 1, it doesn't have to start with n equals 1. Okay, this sequence, 1, 4, 9, 16, this particular sequence appears to consist of the squares of the natural numbers in ascending order. So if that is what that sequence is, then we can represent it this way. It's the sequence of the terms n to the second, where n ranges from 1 to infinity. This sequence, 2, -1, 2, -1, well, we're just alternating between +2 and -2, +2 and -2. So you can write this as 2 times -1 to the n plus 1. You'll see a number of sequences that alternate like that. So the way that you can express it in shorthand is to raise -1 either to n plus 1 or n, depending on whether you start with a negative or a positive. See if you can find a formula for this sequence, assuming that it follows the same pattern that we begin with. 2 over 3, 3 over 9, 4 over 27. What would the next term be, do you think? Yeah, 5 over 81. Yeah, 27 times 3.
That would make the sequence n plus 1 over 3 without n.
Yeah. So if we start with n equals 1, we're not required to, but if we start with n equals 1, then the numerator is 2, so n plus 1. If we start with n equals 1, n plus 1 is 2. And then 3 to the first is the denominator, and so on. Yeah, so it looks like if we just define a sub n as having a numerator of n plus 1 and a denominator of 3 to the n, you can always test your formula just to see if it makes sense. So we can do that for a couple of them. When n equals 1, replace n with 1, we get 1 plus 1 is 2, 3 to the first is 3. I'm sure you all see what's going on, but we'll just go through the motions here. When n equals 2, the numerator 2 plus 1 is 3. The denominator 3 to the second is 9. And that's a match, and so on. So yeah, it looks like this is the formula for the nth term. So we could just use this notation, bracket n plus 1 over 3 to the n, bracket. You could leave it this way. If you want to make sure that you start with n equals 1, you could start this way, n equals 1 to infinity. Okay, the next sequence, 6 over 5, comma, 26 over 25, comma, 126 over 125. If we start with n equals 1, what does it look like a sub n is in this case?
5 to the n plus 1 over 5n, or 5 to the n.
Okay, yeah. 5 to the n plus 1 divided by 5 to the n. So it works when n equals 1. When n equals 1, 5 to the first plus 1 is 6. 5 to the first is 5. And so on, yeah. So that one works. Another way to write this is probably, I would vote for this as being the best way, but you could write it as 1 plus 1 over 5 to the n. This does make it a little more confusing, I think, but it could be written that way. Let's just go with the most straightforward one. Okay, some sequences don't have a formula for the nth term. For example, if the sequence a sub n or if a sub n is the nth decimal place of the number pi, then the first few terms of that sequence are 1, 4, 1, 5, 9, and so on. So if there is a formula for that, no one has discovered it. Some sequences may be defined recursively. So here's an example. If we start with a sub 1 equals 5, and then a sub n plus 1 is equal to a sub n squared minus 2 times a sub n for n greater than or equal to 1. So recursively just means that after you have at least one of the terms defined, then the subsequent terms are defined in terms of prior terms. So if a sub n plus 1 is equal to a sub n squared minus 2 times a sub n, then a sub 2 is found by squaring a sub 1. So a sub 1 is 5, so 5 squared, and then we subtract 2 times a sub 1, and then do the arithmetic. 25 minus 10 is 15. The recursive sequences are sort of tedious to work with, but we will encounter some of those along the way. Some sequences can be pictured by plotting points on a number line or in a two-dimensional plane. So when you're reading in the textbook, pay attention to figures 1 and 2 on page 695 that illustrate sequences that are pictured by plotting points either on a number line or in the two-dimensional plane. Okay, here's our first definition regarding sequences. A sequence a sub n has the limit capital L, which represents a finite number, if the terms a sub n can be made arbitrarily close to L for sufficiently large n. Notation for that: if the limit of a sub n as n approaches infinity equals L, then we just write it this way. You'll also see it this way: a sub n approaches L as n approaches infinity. And then some terminology that you've seen before or heard before. If the limit of a sub n as n approaches infinity exists as a finite number, then we say that the sequence of a sub n terms converges or is convergent, and then otherwise the sequence diverges. Okay, on the next page, another definition regarding the limit of a sequence. So this one says a sequence, a sub n, has the limit capital L, a finite number, if for every epsilon greater than 0, there is a corresponding integer capital N such that if lowercase n is greater than n, then the absolute value of a sub n minus L is less than epsilon. So I'm not sure how many of the epsilon delta proofs you did in Calculus 1. We're not going to do any of those proofs in this class, but whatever you learned in Calculus 1 will help with understanding what we're talking about. But anyway, this is a formal way to prove that a limit, or that a sequence has a limit L. Okay, but do recall from Calculus 1 the meaning of this: the limit of f of x as x approaches infinity equals L, where x is a real number in the domain of f. So the following is a useful theorem that connects the limit of a function of x to a corresponding limit of a sequence. And the sequences are a function of n, where n is a natural number. Okay, so if the limit of f of x as x approaches infinity is equal to capital L, and if the function f evaluated at an integer n is equal to a sub n, then the limit of the corresponding sequence a sub n as n approaches infinity will also equal L. Seems to make sense. So normally, if we're taking the limit of f of x as x approaches infinity, x is all of the real numbers along the way. And for a sequence, we're not picking up all of the real numbers, we're just picking up the integer points. So it makes sense that the limit would be the same. Okay, another thing from Calculus 1, if r is greater than 0, then the limit of 1 over x to the r as x approaches infinity is 0. So by Theorem 3 above, we can apply this to sequences. If the terms in a sequence are 1 over n to the r, where n is a positive integer, and if r is greater than 0, then that sequence converges to 0. So this is stated explicitly on page 697, labeled equation 4. The limit of 1 over n to the r as n approaches infinity is equal to 0 if the exponent r is greater than 0. Okay, now let -1 be less than r, which is less than or equal to 1. So remember from Calculus 1, the limit of r to the x as x approaches infinity, that is equal to 0 when r is strictly between -1 and 1. When r is equal to 1 itself, then the limit of 1 to the x is equal to 1. But if the base number is strictly between -1 and 1, then r to the x approaches 0 as x approaches infinity. Okay, so by Theorem 3, the sequence r to the n converges to 0 for values of r that are strictly between -1 and 1. And this sequence converges to 1 if the value of r is 1. So that's sort of a trivial case when r is 1. Okay, definition 5. We say that, or when we write that the limit of a sub n as n approaches infinity, if we write that it's equal to infinity, it just means that for every positive number capital M, there is an integer capital N such that if lowercase n is greater than capital N, then the nth term of the sequence a sub n is greater than m. Okay, remember the notation, if the limit is equal to infinity, that just means it's divergent. In particular, we say that it diverges to infinity. In other words, the limit does not exist. Even though we write that the limit is equal to infinity, it's just an understanding that the limit does not exist. It diverges to infinity. Okay, some of the limit laws that you learned in Calc 1 will be helpful in evaluating sequences. So this pretty much mimics what you learned in Calculus 1 for limits. So if these two sequences, a sub n and b sub n, are both convergent, and if c is a constant, then the limit of a new sequence, we can form a new sequence by adding those two sequences. The limit of the sum of a sub n and b sub n is equal to the limit of a sub n and the limit of b sub n as n approaches infinity. We also get equality with a difference. The limit of a sub n minus b sub n as n approaches infinity is equal to the limit of a sub n as n approaches infinity minus the limit of b sub n as n approaches infinity. If you multiply each of the terms in the sequence by a constant c, you can move the constant out front, and so it will be c times the limit of a sub n. And then the limit of a constant is itself. The limit of a product, a sub n times b sub n, is the product of the limits. The limit of a quotient is equal to the quotient of the limits, provided that the limit of the denominator does not equal 0. And then finally, the limit of the powers of the terms in the sequence is equal to the power of the limit of the sequence if p is greater than 0 and a sub n is greater than 0. So these probably bring back memories from Calc 1. Okay, we have what is called the squeeze theorem for sequences. So this works the way that you would hope it would. If the terms in the sequence a sub n are less than or equal to the terms in the terms b sub n in the sequence, which is less than or equal to c sub n, and if this occurs for some n greater than or equal to some integer n sub 0, and if the limit of the sequence a sub n is equal to the limit of the sequence c sub n, which is equal to L, then the sequence in the middle, b sub n, will have the same limit. Seems to make sense. Okay, here's a theorem. If the limit of the absolute value of a sub n is equal to 0 as n approaches infinity, then the limit of the sequence a sub n is also equal to 0. So let's just do a sketch of a proof. If we let epsilon be greater than 0, then we're given, since we're given that the limit of the absolute value of a sub n is equal to 0, we're given that there exists capital N such that lowercase n greater than capital N implies that the absolute value of a sub n minus 0 is less than epsilon. So this is what it would mean for the limit of the absolute value of a sub n to be equal to 0 as n approaches infinity. So this is given information, but we note that the absolute value of a sub n minus 0 is just the absolute value of a sub n. But the absolute value of a sub n is just the absolute value of a sub n. And the absolute value of a sub n is equal to the absolute value of a sub n minus 0. And this must also be less than epsilon, right? Because we started out with this, it's less than epsilon, and we showed that the absolute value of a sub n minus 0 is less than epsilon. And this implies that the limit as n approaches infinity of the a sub n terms is also equal to 0. Okay, we're not going to do proofs in this class, but this is just a simple proof. But the main thing you should remember is this theorem. This will be useful to remember as we go. Okay, Theorem 7 on page 699. This is also going to be helpful. If the limit of a sub n as n approaches infinity is equal to L, and if the function f is continuous at L, then the limit of f of a sub n as n approaches infinity will be equal to f of L. So remember this. The limit of f of a sub n as n approaches infinity is equal to f of the limit of a sub n as n approaches infinity, which is equal to f of L. So we'll apply that in this example. So here we have the limit as n approaches infinity of cosine of a sequence. So using Theorem 7, we can write this as the cosine of the limit as n approaches infinity of pi times n plus 1 over 2n. So we'll simplify the rational expression pi times n plus 1 over 2n. So cosine of the limit as n approaches infinity. So pi n divided by 2n is pi over 2, and then plus 1 over 2n. And then when we compute the limit, what do we get? Pi over 2 is a constant, and it's unaffected by n. So pi over 2 remains. And what about 1 over 2n as n approaches infinity? Yeah, it goes to 0. As n gets large, 1 over 2n gets small. So the limit of 1 over 2n is 0. So we get cosine of pi over 2, and cosine of pi over 2 is 0. Okay, the next definition on page 700, definition 10. This is pretty simple. A sequence a sub n is called increasing if a sub 1 is less than a sub 2, which is less than a sub 3, and so on. It is called decreasing if a sub 1 is greater than a sub 2, which is greater than a sub 3, and so on. Seems to make sense. A sequence is called monotonic if it is either increasing or decreasing. Sometimes you'll specify by saying monotonically increasing or monotonically decreasing. Okay, the next definition is also pretty easy to understand. A sequence a sub n is bounded above if there is a number capital M such that a sub n is less than or equal to m for all terms in that sequence, for all n greater than or equal to 1. The sequence is bounded below if there is a number lowercase m such that lowercase m is less than or equal to a sub n for all n greater than or equal to 1. And then if the sequence is bounded above and below, we just say that the sequence is bounded. It's a bounded sequence. It's bounded both below and above, if it's bounded. All right. Theorem 12. The monotonic sequence theorem, page 702. This says every bounded monotonic sequence is convergent. So you can read the proof on page 702. We're not doing proofs in this class, but it might be good for you to read it. The proof of Theorem 12 is based on what is called the Completeness Axiom for the set of real numbers. The Completeness Axiom states that a non-empty set of real numbers that is bounded above has a least upper bound, and that a non-empty set of real numbers that is bounded below has a greatest lower bound. So the essence of this completeness axiom is that there is no gap in the real number line. So that is, every point on the real number line corresponds to a unique real number. Okay, so if there are no gaps, if a sequence is monotonic and, say, bounded above, it has to have a least upper bound, which will be what that monotonic sequence converges to. Here we have less than a minute. Let's see if we can find the limits of these sequences. If the nth term of this one, a sub n equals 3n plus 5 divided by 6n minus 1, and if n goes to infinity, what's the limit? You might remember from Calc 1 a technique for computing limits. So identify the term with the largest exponent in the denominator. So we have 6n. So if I multiply the numerator by 1 over n and multiply the denominator by 1 over n. I'm just multiplying by 1, right? 1 over n divided by 1 over n is 1. So when I multiply the numerator by 1, I get 3n times 1 over n is 3 plus 5 over n. And in the denominator, I get 6 minus 1 over n. And as n goes to infinity, 5 over n goes to 0, and 1 over n goes to 0. And the numbers that are unaffected by n are 3 divided by 6, or 1/2. So the limit of that sequence equals 1/2. Okay, that's all we have time for today. We'll do the other sequences tomorrow, or on Friday, to start with.